Hi, my name is Tommi Gröndal. I'm from Aalto University in Finland, and I'm presenting the work of myself and Professor Ashokan from University of Waterloo on writing style transfer. Natural language processing techniques allow the de-anonymization or profiling of anonymous authors. This is called stylometry. To defend against profiling, the author can perform style transfer. There are two main goals. First, preventing profiling, and secondly, retaining the original semantic interpretation of the text. We show that prior approaches mostly fail at combining these two requirements. We propose a new style transfer technique called part choice, which markedly improves over baselines in semantic retainment while at the same time retaining a good style transfer performance. I'll first talk about the problem statement and some prior research, and then present the part choice technique. I will then go through the main results from our experiments, focusing on comparing part choice with baselines on sentence-based datasets. Finally, I'll summarize some of the take-home messages and present some pointers for future work. Starting from the problem statement, stylometry can be used to identify authors by writing style or profile them based on some property like gender or age. Features typically include word or character n-grams or grammatical features such as those pooled under the right prints group. The availability of these stylometry techniques allows an adversary to use them for de-anonymization or profiling of deliberately anonymous authors with potentially harmful or even dangerous consequences to these authors. To defend against this, the author can do style transfer to change the writing style of the original text in such a way that aims to change the prediction made by the author profiler the adversary uses. A second very important criterion for style transfer is that the semantic interpretation of the original text is retained to a maximal extent. Current approaches to style transfer tend to fall in two camps. Encoder-decoder networks are sequence-to-sequence architectures, typically using recurrent neural networks like LSTMs. They try to produce a style-neutral latent encoding of the input and then decode it to the target style. Even though they're currently the dominant approach to style transfer, they exhibit quite poor semantic retainment and also require separate training for each dataset. Rule-based paraphrasing allows better control of semantic retainment, but tends to have a limited applicability. Our technique is called paraphrase choice or part choice, and it combines multiple paraphrasing techniques to generate a large number of candidates. It can be used with many different selection schemes for choosing the best performing paraphrase depending on the task. We compare part choice across multiple datasets with 3 encoder-decoder baseline techniques and 2 rule-based baseline techniques. We demonstrate that part choice has the best combined effect of style transfer and semantic retainment. Now I'll go through the main aspects of the part choice technique. It has 2 parts. First, paraphrase generation, which produces a large number of candidate paraphrases and is independent of the style transfer task. Secondly, paraphrase selection, which is a task-specific selection from among the candidate paraphrases based on how well they're able to evade a surrogate profiler, which can be the same as or different from the targeted author profiler we aim to evade. The paraphrase generation task can be divided to 3 parts. For grammatical transformations, we use passive to active, negative to affirmed, and question to declarative transformations, with some additional material to retain the original meaning of the sentence. For example, a yes-no question like "Did John see Mary?" could be paraphrased as "Is it true that John saw Mary?" As external knowledge bases for paraphrase replacements, we use PPDB and WordNet, and we also use a small set of simple rules that we have programmed ourselves, dealing with things like modal auxiliaries and punctuation. To further increase the readability of the output, we filter out ungrammatical output from PPDB by syntactic context information, and use a corpus-based technique for inflecting originally uninflected lemmas from WordNet. For typos, we go through the target style examples of the original training set and gather a dictionary from correctly spelled words to their possible misspellings via SimSpell in that corpus. In paraphrase selection, we choose the candidate that minimizes the likelihood of the surrogate profiler classifying it as the actual class. We experimented on 3 different types of surrogate profiler. With query access, the surrogate profiler was the same as the targeted author profiler itself. With data access, the surrogate profiler had a different architecture but the same training data as the targeted author profiler. With surrogate access, the surrogate profiler differed from the targeted author profiler in both architecture and training data. We conducted multiple experiments across different types of data and tasks. In this presentation, I'll specifically focus on our results from two-class sentence-based style transfer experiments. These experiments were conducted on 4 datasets, and part choice was compared with 3 baselines. There were 2 larger datasets of around 2.5 million training examples for the profiler, consisting of gender-labeled Yelp review sentences and age-labeled blog post sentences respectively. The 2 smaller datasets are labeled by author identity. Alice Bob contains blog post sentences from the blog age dataset by only 2 authors who we call Alice and Bob. Trump Obama contains sentences from political speeches by the 2 most recent US presidents. We divided each training set to a separate profiler training set and a surrogate training set. The size of the surrogate training set was always 15% of the size of the profiler training set. All 3 baselines in these sentence-based experiments were encoder-decoder techniques. The cross-aligned autoencoder or CAE baseline is an autoencoder that uses a technique called cross-alignment for enforcing that the encodings coming from different source styles are aligned in the latent space. It then decodes text in the target style from this latent encoding. Back translation or BT is similar to CAE, except instead of cross-alignment, it uses back and forth machine translation for attempting to align the encodings from 2 target styles. For determining the style, it queries a CNN classifier that we also used as an auto-profiler in our experiments. A4NT is a generative adversarial network or GAN that trains a decoder to generate text in the target style while at the same time training a classifier to correctly detect the style from the decoded text. It also includes a reconstruction loss from the original text that results in minimizing changes to the original to only those that are relevant for the style transfer. As the classifier architecture, it uses an LSTM, which we also use as one of our auto-profilers prior to the GAN training. We compare the baselines to 6 part choice variants overall that differ in paraphrase selection and the access assumptions to the auto-profiler or its training data. First, we experiment on query access to each of our 3 author profilers, which we will present in a forthcoming slide. There's an LSTM profiler, a CNN profiler, and a write-prints profiler. As our separate surrogate profiler architecture, we use word unigram-based logistic regression. We have 2 variants of this surrogate profiler. The first one trained on the same training data as the targeted auto-profilers, and the second one trained on the separate surrogate training data that we discussed before. Finally, we also experimented on fully random paraphrase selection that had no access to anything. On this slide, we show meteor scores between original and transformed sentences by each style transfer technique on all 4 datasets. Meteor measures n-gram overlap with additional synonym and paraphrase information. The CAE and BT baselines always result in the worst scores, shown here in red. In the smaller datasets Alice Bob and Trump Obama, CAE and BT don't even exceed 10 in meteor scores, which practically means absolutely no semantic retainment. A4NT received quite good scores in the large datasets Yelp gender and blog age, but significantly declined in the smaller datasets. On manual evaluation, it received no semantic retainment on these datasets, in this respect corresponding to CAE and BT. In green, we have shown those part choice values that are higher than any of the 3 baselines. In all datasets except blog age, all variants of part choice exceed all baselines. In all datasets, part choice CNN gets the highest score among all techniques compared. While there was some variation between different part choice techniques, overall part choice received similar scores between 40 and 50 in all datasets. Contrasting all 3 baselines, part choice's performance was not negatively affected by dataset size. This is because part choice's paraphrase generation is completely independent of the dataset and only paraphrase selection is task specific. For evaluating style transfer, we measured the accuracy decrease, that is how much original accuracy went down after style transfer. As mentioned before, we used 2 deep learning classifiers, a CNN and an LSTM, both of which use words as input features. The BT baseline and the part-choice CNN variant query the CNN classifier, and the A4NT baseline and the part-choice LSTM variant query the LSTM. We additionally use the multi-layer perceptron classifier trained on the right prints features. We query this with the part-choice right prints variant, but no baseline queries it. Original accuracies on each dataset are shown here. With all profilers, these were the lowest for blog age and the highest for Alice Bob. The two deep learning classifiers had the overall best profiling accuracy and usually functioned very similarly, except in Trump-Obama where LSTM clearly performed better. This slide shows the accuracy decreases with each profiler and each style transfer technique on the two larger datasets, Yelp gender and blog age. Unsurprisingly, part-choice random that performed no targeted paraphrase selection always had the lowest score. However, if part-choice random is discarded, the lowest performance was always obtained by A4NT, as shown here in red. In green, we again show those part-choice results that exceed all three baselines. In the deep learning classifiers, all variants of part-choice except random and right prints always exceed all baselines. The highest results, unsurprisingly, are obtained with query access to the profiler. Query access to right prints always gives part-choice the best performance on the right prints classifier, and in Yelp gender the part-choice LSTM variant also outperforms all baselines. Here are the accuracy decrease numbers from the two smaller datasets, Alice Bob and Trump-Obama. Unlike in the larger datasets, here the CAE and BT baselines do very well in style transfer, especially in Alice Bob. However, when we recall that neither exceeded 10 in Meteor score in these datasets, these results are less surprising. Manual evaluation confirmed that on these datasets, these techniques simply produced completely novel text with no relation to the original at all, therefore not being usable for style transfer. Due to the complete lack of semantic retainment by CAE and BT, it makes sense to focus on the comparison between A4NT and part-choice here. Excluding part-choice random, here we have highlighted in blue all values that exceed A4NT with any variant of part-choice. In Alice Bob, all variants of part-choice exceed A4NT in all but two cases in which they are tied. In Trump-Obama the situation is more mixed. A4NT performed very well on the LSTM, although so did part-choice LSTM. However, on the CNN, A4NT's performance drastically dropped from the LSTM, being exceeded by three variants of part-choice and reached by the surrogate variant. In right prints, A4NT outperformed all part-choice variants except query access to right prints, which clearly reached the highest result. We draw the following main conclusions from our sentence-based experiments. Only part-choice was able to retain semantics on the smaller datasets, all baselines failing at this. Second, across all four datasets, part-choice was always able to reach the highest score. Finally, while there was some variation between different variants of part-choice and different datasets, part-choice's overall performance was nevertheless similar across all experiments. This was a striking contrast to the baselines, which performed very differently on the larger datasets and the smaller datasets due to their dataset-specific training. In profiling accuracy decrease, all variants of part-choice outperformed all baselines on the larger datasets, Yelp gender and blog age. This was true even of the surrogate variant that had no access to either the architecture or training data of the targeted profilers. Comparing part-choice to A4NT, which was the best performing baseline in semantic retainment, the LSTM variant of part-choice outperformed A4NT in almost every test. This is the most fair measurement between part-choice and A4NT, as the LSTM variant replicates exactly A4NT's query access to the LSTM profiler. However, even the surrogate variant of part-choice outperformed A4NT in a clear majority of tests. Here are some example transformations by the baselines and the surrogate variant of part-choice, first from the Yelp dataset. We've colored out those words that the techniques have changed from the original. CAE and BT clearly take meaning away from the original, as shown here in red. A4NT is quite conservative in the changes it does due to the reconstruction loss, and the changes are more semantically appropriate. Part-choice does more transformations, which have a clear semantic similarity to the original. These examples are from one of the smaller datasets, Trump-Obama. Here CAE and BT completely change the meaning of the original, and BT doesn't even result in a grammatical sentence. A4NT again retains much of the original. Here the change it brings is clearly semantically inappropriate. The part choice example on the last row is somewhat exceptional in having so many changes in one short sentence. We can see the passive-active grammatical change along with appropriate adjustments to the pronoun case, a change in the modal auxiliary, and an addition of a particle well. This example quite nicely shows the potential of part choice. Moving on to our experiments on document-based data, here I will only present summaries of our results. We conducted these experiments on 4 datasets derived from the Brennan-Greenstat and extended Brennan-Greenstat corpora. None of the encoder-decoder baselines are applicable for multi-sentence documents. Instead, we used 2 rule-based baseline techniques called PAN 2016 and Mutant X. For the part choice variant in these experiments, we replicated the paraphrase selection scheme from Mutant X, which is a genetic algorithm. In addition to using part choice alone in this way, we also combined the 2 best performing techniques, which were part choice and Mutant X, first running part choice on all documents, and then running Mutant X only on those documents that had not yet been transformed with part choice alone. Unlike with the encoder-decoder baselines in the sentence-based experiments, here no technique failed at semantic retainment. However, part choice univocally received the best results in all evaluations. Even though the combination of part choice with Mutant X did not achieve as high results as part choice alone, it always outperformed Mutant X alone as well as the PAN 16 baseline. However, in style transfer the results were not as good for part choice, as it did not manage to outperform Mutant X alone. However, the combination of part choice and Mutant X always achieved the highest result. Therefore, by combining part choice with the best performing baseline, Mutant X, we were able to improve on this baseline in both semantic retainment and style transfer. Finally, I'll briefly review a countermeasure to style transfer. We tested whether the adversary could use the same style transfer technique for training the profiler with transformed data. This is called adversarial training. We applied the transformations to the original training data and combined the original non-transformed training data with this transformed variant. We did these experiments on the AliceBob dataset with the LSTM profiler that received a high original profiling accuracy of 91%. First, on the original non-transformed test set, while adversarial training with most techniques resulted in a negative effect on original profiling accuracy up to 15%, accuracy still remained relatively high compared to the original 91%, but with part choice random they were clearly the lowest. We then evaluated profiling accuracy on the transformed test set with the same transformation technique as used for the adversarial training itself. Here we saw a large accuracy increase with all techniques except part choice random. We achieved generally slightly lower but still clearly comparable accuracies to the accuracy on the original non-transformed test set. However, very interestingly, with part choice random, this accuracy goes way down. So even though part choice random was not a good style transfer technique because it didn't result in a good accuracy decrease, it was highly resistant toward adversarial training as a countermeasure, actually taking both original tested accuracy down and transformed tested accuracy down even more. It therefore seems that adding randomness to the style transfer process can help protect against adversarial training as a countermeasure. We summarize our main claims as follows. We were able to improve baseline performance in multiple respects. First, we always achieved the highest semantic retainment results compared to all baseline across all datasets and all test settings. Secondly, the combined effect of style transfer and semantic retainment was overall highest with part choice. Finally, the overall success of part choice indicates that our paraphrase generation was able to produce a large variety of paraphrases usable for many different tasks and across different data types. However, a problem for both the baselines and part choice was adversarial training as a countermeasure. Therefore, while we were able to combine strong semantic retainment with good style transfer performance, an open question for future research is combining these with resistance to adversarial training. Our results suggest that it might be beneficial to increase the randomness of the style transfer process. Thank you, and we encourage you to visit our group website.